Alright, gang, here we go. This is for Physics, Unit 7, Part 1. Talking all about simple harmonic motion. Should be lots of fun here. Alright, so to start off, I just want to look at this real quick, and we'll kind of answer these questions as we go. But it might be beneficial for you to pause the video and take a gander at this and just try to think about what might be going on. So just setting up what's happening here is you've got some sort of spring system here. And so at B, this would be its relaxed state. So it's attached to some wall, and then you've got a mass like a brick or a piece of wood or something that's moving back and forth. Okay, and so it kind of flip-flops between these three spots, right? So this is its relaxed state, and it gets stretched out, and then the spring pulls it back to center, and then it goes this far, and then it comes back this way, right? And you kind of go just back and forth, all right? So that's kind of the systems that we're looking at today. This harmonic motion where we kind of go back and forth, back and forth. All right, and we're going to be looking at all of these different ideas: forces and velocities, accelerations, kinetic potential, and mechanical energies. Should be lots of fun. All right, so first of all, we need to look at this thing called Hooke's law. All right, so Hooke's law allows us to calculate the spring force, so the elastic force. Okay, it's the force that keeps our object in this motion. Okay, and it's equal to negative kx. All right, where k is the spring constant. We've looked at spring constants before. It's essentially how hard the spring is, or how stiff the spring is. And then x is your displacement. And remember, your displacement is your initial minus your final, right? So how far have you gone? So you need to know both your initial length of the spring plus how much farther you went. Okay, so so the force, elastic, that's the restoring force, okay, to the equilibrium position. Now you need the minus sign because because the displacement and the restoring force are always going to be opposite one another, right? Because if you think about it, this brick here, this mass, is moving to the left, right? Or the displacement would be, we could define this if this is 0, right? And then we'd have, this might be like +5, okay? And then this would be -5 right over here, right? Okay, and so this would be +5 over here. So anyway, so you got 0, all right, and you've got -5, but your restoring force, the spring, is going to be pushing it back this way. That's going to be your elastic force is going to be pushing it this way. Notice that your displacement was negative, but your elastic force is going to be to the right, which is positive. And then when you're over here, you're at +5, but your elastic force is going to be to the left, right? So it's going to be negative, okay? All right, so it's always going to be opposite. Okay, K is the spring constant, and it's in newtons per meter. Okay, newtons per meter, and then K measures the strength of the spring. All right, let's just do a quick little practice problem here. It says a slingshot consists of 2 rubber bands that approximate a spring. The equivalent spring constant for the 2 rubber bands combined is 1.25 times 10 to the 3rd Newton meters. How much force is exerted on a ball bearing in the leather cup if the rubber bands are stretched a distance of 2.5 centimeters? All right, so Hooke's law here, force elastic is equal to negative k times x. All right, so your force elastic is equal to negative k. Well, your k value, they tell us right there, is 1.25 times 10 to the 3rd Newton meters. Okay. And then it tells us our x value. This is the distance it's stretched, but the problem is that's in centimeters, but you need it in meters. So we need to get our centimeters into meters, so we divide by 100, so it becomes 0.0250 meters. All right. So we just take 1.25 e to the 3rd times 0.025. We get 31.3, and meters cancel, and we just end up with newtons. So 31.3 newtons. Well, negative 31.3 newtons. All right, and that just tells us the direction. All right, and so really it says how much force is exerted. So it would be the positive 31.3, which is the answer we have somewhere right there. All right. Simple harmonic motion. So this gets us to this idea of simple harmonic motion. Okay, and anytime we have a system that obeys Hooke's law, all right, or this idea that we have a force that's related to our displacement by some constant, that's Hooke's law. Okay, anytime we have this back and forth motion around an equilibrium point, okay, we are going to have what's called simple harmonic motion. And simple harmonic motion, not only is it nice because it's simple, but it also obeys very specific rules for velocity and acceleration based on this formula here. Okay, so that's really why we care about simple harmonic motion, because it allows us, if we can establish a system that is in simple harmonic motion, it allows us to make very specific generalizations about its motion. All right. So let's look at some of those. So we've got the same setup, right? We've got equilibrium position where our x equals 0, and then we've got some positive x and some negative x this way, and the force, all right? So they kind of tell us all these things. So it says, where's the force maximum? Well, we've got a couple formulas that we need to keep track of, right? So we've got Hooke's law, which equals negative kx. Well, k is never going to change, right? So that's our positive value. Okay, or that's some constant that's never going to change, okay? And then we've got our x value, all right? So where's its maximum? So really, when they say maximum, really we're looking for magnitude in all of these things, all right? So where's its magnitude? Well, or where's the magnitude maximum? Okay, well here, our x is equal to 0, so that tells us that our constant times that 0 is going to be, our force is going to be equal to 0, so it can't be b. At a and c, the x values are the same, but they're just opposite in direction, right? One's x and the other one's negative x. Okay, so they're the same but in opposite directions. So therefore, a and c is when our force is going to be maximum. All right, both of these values right here. All right, and it says, where is the force 0? Well, the force is 0 when our x is equal to 0. Okay, so that has to be at equilibrium positions where our force is 0. So where is the acceleration maximum? All right. Well, think about it this way. We also know that force is equal to mass times acceleration. Okay, so we've got the same sort of situation here. Okay, where our force is equal to some constant or mass. We're not changing the mass of this brick, equal to the acceleration. Okay, and so we've got, so when is our acceleration going to be maximum? Well, our acceleration is proportional to our force. So when our force is really big, our acceleration is also really big, right? So when our force is maximum, our acceleration should also be maximum. Okay, and so we see that our acceleration is maximum a and z. The acceleration is 0 again when the force is equal to 0. All right, now where is the velocity maximum? Well, this is where things get more interesting. All right, so think about it this way. All right, so we're looking for maximum velocity. Now, take a step back for a second and think about parabolic motion or projectile motion. Remember, I had our projectile motion. At the beginning, at this point, we had some horizontal vertical velocity. Remember, horizontal velocity never changed, but the vertical velocity started off with some positive value that was going off this way, positive, right? And then as it went up, that vertical velocity went lower and lower until when we get here, our velocity in the y direction was equal to 0. Remember that? Okay, and then as we go back down, our velocity in the y direction gets bigger and bigger until we're, some big value going down this way. But remember, at this peak, our velocity in the y direction equals 0. Okay, so same thing happens here. Now, why was this equal to 0? Well, this was equal to 0 because we were changing directions. All right, so same thing happens here when our object is motioning, and you can imagine something bouncing on a spring going up and down. When it goes down, and then when it starts coming up, it starts changing directions. So as it starts changing directions, the velocity is going to be equal to 0. So right here at A and C, our velocity is equal to 0, and directly in the middle is when we're going to be moving the fastest. Okay, so our maximum velocity is going to be at B, and then the velocity of 0 is equal at A and C. Now, this also makes sense if you think about it this way. All right, if you have this thing moving, okay, when it's out here, you've got this force that's pulling it back towards the center. Now, as this block gets closer towards the middle, this force becomes less and less because the displacement is less and less, and we know that force is proportional to the displacement. So as it gets closer, this force gets smaller until we reach the point where the displacement is 0, but we've got inertia, right? That's going to keep it going. So it's going to keep going this way. Okay, and we're at an equilibrium. It's going to keep traveling to the left, but as we start going to the left, we get a displacement in the opposite direction, so the force elastic starts to push it this way and starts to slow down. So we can see that when we started here, our velocity is equal to 0, and as we move towards equilibrium, because of this force in the same direction as our velocity, okay, it's making us go faster until we reach the point where our force is equal to 0, and then as we keep going past, the force is in the opposite direction of the velocity, and that makes us slow down. All right, until we reach 0 again. Okay, and we kind of go back and forth like that. All right, now Hooke's law graph. Now in class, what we did is we probably created a graph with a spring, and we got these values where we graphed newtons here and the meters here. We took a spring and we put different masses on it, and then we graphed it out, right? And we marked these points like so. And we recognized that all of these points, as we placed our different masses on the spring, we formed these x's that was pretty much in a straight line. Okay, if I could draw a straight line, that'd be a lot better. So we had this line of best fit. Remember, then we found the slope of this line, right? And remember, slope is equal to the change in y over the change in x. Okay, and our units for the y value were in newtons. Okay, and the units for the x value were in meters. Okay, so we were in Newton meters. And we found that the slope of this line and the Newton meters were actually the spring constant. Okay, so if we could graph the displacement versus the mass that was placed, we could find the spring constant for our spring. Okay, all right, so that's essentially what we did here. All right, it was pretty nifty, pretty nifty. Okay, last little bit here. Okay, so simple pendulums are also an example of simple harmonic motion. Okay, so don't let this graph confuse you. Let's just look about what's going on real quick. So we've got a pendulum. Okay, this dashed line here, that's its equilibrium point. So ignore all this for a second. Okay, this is its equilibrium part right here. All right, and now this, you've got this tension force that's keeping it attached to the wall. That makes sense because that's just the string. Okay, now when you swing out, if you take a pendulum, right, you take it, you know it's going to drop and it's going to come back and it's going to keep going back and forth like this. Now, what we care about is this restoring force, and it acts very much like the spring. It follows Hooke's law. All right, so as you pull it out, you've got some component of the gravitational force that's going to be pulling it back towards center, back towards that equilibrium. So you got this tension force pulling it back up towards the ceiling, and you've got this restoring force that's pulling it back towards the center. And the same idea here, as this thing gets closer to the center, the restoring force gets weaker until the restoring force is equal to 0, and then it swings back the opposite direction, back and forth, back and forth. Now, the cool part about this is that we can actually, if we take these values and draw another perpendicular value here, showing us the force of gravity, we can find this component in the x direction and the component in the y direction, and then we can actually find the value of this restoring force if all we know is the force of gravity on the ball time and the theta value here, and then we can find the restoring force just by using our sine value, right? Because we know that sine is equal to sine of theta would be equal to opposite over adjacent, or opposite over hypotenuse. So the opposite here, right, and it would be the FG in the x direction, and then the hypotenuse would just be the FG. So let's do a couple practice problems. It says, find the restoring force at 3 degrees, 9 degrees, 27, and 81 if f of g equals 10. Well, we just established our formula in the last slide. We said that the sine of theta would be equal to fg in the x direction, because that's our restoring force, over fg. Right? Because that's the restoring force, because the fg of x is the part that's trying to restore us back into equilibrium. And so we want to find this restoring force. All right, well, so that means fg of x would be equal to fg times our sine theta. All right, and then we can just plug these values in. Our fg is always going to be 10, and then our sine theta is going to be these three values here. All right, so if you do all that, you should get these values here. You take, make sure your calculator's in degrees, not in radians if you're, okay, and taking trig or something right now. So you plug 10 in, so 10 times sine of 3, and 10 times sine of 9, 10 times sine 27, 10 times sine 81. Plug those in and you should get these values here. All right. Now, it says, are the forces proportional to the displacement? Now, this is kind of interesting. Notice that as we go, okay, our degrees here increase by 3, okay, and you can see that from here to here, all right, that the newtons also increase by 3. All right, so yeah, it's pretty proportional at that point here. And then as we go from 9 to 27, let's see, is it proportional? So that's another change of 3, so we can take our 9.88, 4.54 divided by our 1.56, and it's proportional, should be around 3. I got 2.91, so that's pretty proportional. What about the next one? So 81 to 27, so that's another 3. So if we take well, we don't even need to do that. If we take 9.88 divided by 4.54, you know you're going to get something around the lower end of 2, right? So everything's proportional up until the 81 degrees, which is exactly what we discussed earlier, right, when we talked about simple harmonic motion here. It says small angles fg of x is proportional to the displacement, or your theta. Okay, so as long as you stay within a narrow degree change, you're going to be following simple harmonic motion, and you'll be able to use Hooke's law, which is essentially this graph here, in order to predict our motion. All right, but once you get past a certain value, you start to veer away from Hooke's law's prediction, and so you get less and less able to predict what occurs. All right, so that's all about simple harmonic motion. Simple harmonic motion is pretty cool, but it can get pretty complex. We just barely scratch the surface. All right, and that's about it. Do your practice problems. Let me know if you have any questions, and I'll see you on the flip side.